A rocket is a bomb that we have all agreed to trust. Think about what a launch really is. Millions of pounds of fuel, lit on purpose, with people sitting on top of it. For 100 years, there was only one way to know whether a rocket would fly or fall. You lit it, and you watched. Sometimes it rose, sometimes it came apart in the sky. Either way, you learned the answer only after it was too late to change it. But imagine a screen where the rocket has already flown, not once, 10,000 times. In most of those futures, it climbs and separates and slips into orbit exactly as planned. In a few hundred of them, 90 seconds after liftoff, it comes apart in a ball of fire. None of it has happened. The real rocket is still on the pad, cold and full and quiet. The crew are still in the building, pulling on their gloves, and a number on the screen says 94%. 94% of the time, they come home. Now. Do you light it? Let me start with something surprising. Not every rocket is a gamble anymore. SpaceX has a rocket called the Falcon 9, and it has quietly become the most reliable machine of its kind ever built. By early 2026, it had flown to space more than 600 times and succeeded on more than 99 flights out of every 100. In a single year, it launched 165 times and delivered its cargo every time. One of its boosters has flown, landed, and flown again 35 times over, the way an airplane returns to the sky the next morning. Watching a Falcon 9 land has become almost boring. For this rocket, the old question, will it blow up, has been quietly answered. Almost always, no. And then the same company built Starship. Starship is the largest rocket ever made, the one meant to carry people to the moon and one day to Mars. And it does something the Falcon 9 no longer does. It explodes. Its early test flights ended again and again in what the engineers, with dry humor, call a rapid, unscheduled disassembly. A polite, technical way of saying the rocket tore itself apart. Twice in a row, in a single year, it lit up the sky over the ocean. Even its newer, larger version in 2026 flew halfway around the planet, then burst into flame coming down. So here is the strange part. The same people, the same genius, the same factory, built one rocket that almost never fails and another that keeps ending in fire. How? The answer is that failure, for this company, is not an accident. It is the plan. Their method is simple and a little shocking. Build the rocket quickly, fly it before it is perfect, let it break, study exactly how it broke, then build the next one a little better and do it all again. Every explosion is not a disaster. It is a lesson, paid for in steel and fire. Flight by flight, the fireballs grow rarer, until one day the rocket is as calm and certain as a Falcon 9. It works, but it is loud, costly, and very public. What if you could learn those lessons without the fire, somewhere no one gets hurt, where the only thing lost is a little electricity? It turns out we already do this, in a small way. Before any serious rocket leaves the ground, it has already flown thousands of times inside a computer. Engineers build a mathematical version of the machine and fly it over and over, changing the details a little each time. A stronger gust of wind, an engine running slightly hot, a tiny flaw in a weld. Then they count how many of those imaginary flights end well. If 9,000 out of 10,000 reach orbit, the rocket is probably ready. If half of them fall out of the sky, it is not. This is real. It is how the risk of a launch is measured today. But today's simulations are still rough sketches of a real rocket. They capture the big forces, not the full, living detail of an actual machine tearing through the air. Now imagine that sketch becoming a portrait. A world model is an AI that does not just store facts about a rocket. It learns how the rocket behaves deeply enough to play the whole event forward, moment by moment. The fuel burning inside each engine, the metal flexing under strain, the heat building on the skin as it falls back through the air. Not a cartoon of a launch, but something detailed enough to feel real. World models like this are not science fiction. Simpler ones already exist. Today, they help a self-driving car picture the next few seconds of traffic before it happens. They build small video game worlds a player can move through, invented on the fly. They give robots a place to practice a task 1,000 times before trying it with real hands. But today's world models are still short-sighted. They are good at the next few seconds, not the next few minutes. Run them too long and they begin to drift, forgetting what they just showed you, inventing things that could never really happen. They can dream a convincing world, but not yet an accurate one. A rocket launch, where one wrong detail ends in fire, is still far beyond what they can faithfully imagine. What changes that is time and scale. Every year, the computers grow more powerful and the models grow sharper, fed on more real launches, more sensor data, more failures. Somewhere in the next decade, those small dreamlike worlds could grow steady and detailed enough to hold an entire rocket in mind, from ignition to orbit, and run that launch all the way to the end without losing the thread. Feed such a model one specific rocket on one specific morning with that day's weather and that week's tiny imperfections, and it could fly that exact launch 10,000 times before you ever light the real one. And there is something eerie here. The same kind of company that builds the rocket now also builds the mind that watches it. But here is the part that matters most, and the part that is easy to forget. Even a perfect model does not answer yes or no. It can only say, out of 10,000 tries, this many came home. It gives you the odds, not a promise. A weather forecast for a single, unrepeatable morning. And a number like that does something strange to the people who must act on it. Because a model good enough to measure a rocket's chances is also powerful enough to end a dream with a decimal point. A rocket program is enormous, worth more than almost any company on Earth, watched by investors, by governments, by the families of the people who will fly. Everyone reads the same forecast. And if the model says a flight carries a real chance of killing everyone aboard, a quiet question appears. Does anyone ever get to fly at all? This is the trap. A number that was only ever a probability slowly hardens into a verdict. The forecast stops being a tool and becomes a gate. And space has always asked for the opposite. Every first flight meant sailing into the unknown and accepting it might go wrong. A machine built to erase the unknown could, without meaning to, talk us out of going at all. If we only launch what the model blesses, we may never launch the one that mattered. Picture the morning of the first crewed flight to another world. The astronauts are real people. They have names. They are still alive, still training down the hall, still calling home at night. And before any of them puts on a suit, the world model runs their launch, thousands of times. In most of those runs, the rocket climbs, and the crew reach space, and history is made. But in some of them, 90 seconds after liftoff, the rocket comes apart, and everyone inside is gone. The people who love them can watch those runs. The astronauts can watch them too, seeing in perfect detail the version of the morning where they do not come home. The number is good, 94%. And still, the crew chooses to fly. Because someone, in the end, has to be the one that reality tests for real. Now sit beside the launch director, the one person who must say the word that lights the rocket. 94 times out of 100, these people live. 6 times, they do not. There is no button for maybe. There is only yes or not today. And here is the cruel twist waiting on the other side. If the launch succeeds, no one will ever know whether the model was right or whether this was simply one of the 94, and the 6 was always out there, waiting its turn. And if it fails, the words, "it was only 6%, will mean nothing to the people who loved them. Because there is one thing the model can never fully hold. The real rocket has a flaw the simulated one does not. A single weld cooled a fraction too fast. A bird. A gust the sensors never caught. The model can be more detailed than any human mind could picture, and still miss the one small truth that decides everything. It can show you 1,000 convincing explosions and never show you the real one. So let us come back to the launch pad as it stands today. Engineers really do fly their rockets thousands of times inside a computer before they fly them for real. The Falcon 9 really has become that reliable. Starship really is still climbing out of the age of fireballs, one flight at a time. And the hardest steps, refueling a rocket in space, landing people on the moon, reaching Mars, are still ahead of us, with dates that keep slipping and experts who keep warning it is harder than it looks. But no computer today can model an entire rocket flight, in full, across everything the real world might do to it. And there is a limit that may never completely go away. A model can produce a launch that looks utterly real, detailed, violent, convincing, without producing the launch that actually happens. So maybe the question is not whether we can teach a machine to watch a rocket die. We are already learning how. Maybe the real question is this: what happens when a machine can watch a rocket fall 10,000 times, but the one launch that matters is the only one it will never get to see?